This experiment is a synthesis of hexamine cobalt-3 chloride. In this experiment, you will prepare, isolate, and turn in a pure sample of this coordination compound. The chemistry involves a series of steps. You will start with cobalt-2, that is divalent cobalt, and ammonia. First, you'll prepare the hexamine cobalt-2 complex by adding ammonia to the cobalt-2 ion. Next, you'll oxidize this to the cobalt-3 complex with hydrogen peroxide. Some side reactions will also take place, namely the hydrogen peroxide will disproportionate to oxygen and water. In the third step, you'll exchange the hydroxide ion, which came from the hydrogen peroxide, with ammonia. In this process, the ammonium ion you added will act as a buffer to keep the pH from going too high. Finally, you'll precipitate the pure hexamine cobalt-3 chloride by adding an excess of chloride ion. This is an example of the common ion effect. The compound you'll prepare today is called a coordination compound. This refers to the apparent way in which the covalent bonds are produced. The metal or central atom has empty valence orbitals. The ligand has non-bonding valence electron pairs. These orbitals overlap to form a bonding orbital in which the electron pair was donated by the ligand. The cobalt atom has 27 electrons. 18 are in the argon kernel and 9 in the valence shell. The +2 ion is a d7 electron configuration, and the +3 ion is a d6 electron configuration. Both ions have empty d, s, and p valence shell orbitals, and these can be hybridized to 6 d squared sp cubed orbitals, which allow formation of octahedral complexes. We'll now go to the laboratory and start the manufacturing process. The first step is going to be the preparation of the hexamine cobalt-2 complex. So don't forget, put on your goggles, restrain long hair, and off to the laboratory. We'll carry out a reaction in a 150 milliliter beaker. First, tear it on a top loading balance and weigh in the required amount of ammonium chloride. Using a piece of paper, weigh out and add a small amount of powdered activated charcoal. You should be asking yourself, why are we adding this? To this we'll add a measured amount of cobalt chloride solution of known concentration, using this rather fancy looking burette. Set this burette to an initial 0.000 milliliter reading, and now we can pump in the required amount of cobalt chloride. Here it is, exact to greater than 0.01 milliliter. Touch the tip of the burette to the side of the reaction beaker to complete the addition. Gently swirl and warm to help dissolve the ammonium chloride. Now in the hood, cool this down and add an excess of concentrated ammonia. Swirl, and at this point the cobalt-2 complex forms instantly. We'll now oxidize this complex to the cobalt-3 complex with hydrogen peroxide. There will also be some oxygen forming by disproportionation, so you must work carefully. With cooling and swirling, add the hydrogen peroxide in several portions. The cobalt-3 complex which is formed has a hydroxy group on it instead of an ammonia group, and we must now carry out an exchange. We will now use the excess ammonia in solution to exchange the hydroxide ion. In doing this, the ammonium ion, which we added earlier, will buffer the solution by reacting with the released hydroxide ion. But there's a problem. Although cobalt-2 exchanges its ligands very rapidly, the ligand field theory shows that Cobalt-3, which is a low-spin D6 complex, exchanges its ligands very slowly. Now, how are we going to get around this? Well, here's where the charcoal comes in. Charcoal is solid carbon and has an occasional odd electron sitting on its surface. The cobalt-3 complex can sit on the surface of the charcoal and pick up this electron, thus essentially reducing it to cobalt-2, which exchanges ligands rapidly. After the ammonia for hydroxide exchange occurs, the cobalt complex can leave the charcoal surface and the electron remains behind. The complex coming off then is the cobalt-3 with 6 ammonias on it. To carry out this exchange, you'll put the reaction beaker in a warm water bath at about 60 degrees for 5 to 10 minutes. Do not heat too hot, otherwise you'll lose too much of the excess ammonia, which is volatile. A brownish precipitate should form. Cool the beaker to complete the precipitation of the complex. When the beaker is cold, you can collect the precipitate, which is the charcoal in the complex, using your Buchner funnel. This has holes in its base, which you must cover with the filter paper. Turn on the vacuum and make sure the filter paper is seated properly. Collect your precipitated reaction mixture. To purify this material, scrape the collected material from the filter paper back into the beaker. Try to collect as much product as possible, even if you scrape off some lint from the paper. Dissolve this by adding water with some HCl and heating to boiling. Make sure your suction flask and funnel are clean. It's best to use 2 filter papers here. Make sure the filter papers are seated properly. Make sure the suction is on. You will filter this hot solution, but this time save the filtrate and throw away the charcoal. Now, carefully, slowly, pour the hot solution into the center of the funnel to keep the charcoal from creeping under the edges of the filter paper. This is what you will collect and discard. Finally, you will precipitate and collect the hexamine cobalt-3 chloride by adding an excess of chloride ion. This precipitation is called the common ion effect. Heat the solution in the suction flask just to boiling. Then stop heating, wait a few seconds, and add the HCl. You will use HCl as a source of chloride because it is volatile and soluble, and an excess can be easily removed from the product. Swirl and add the contents back into your clean 150 milliliter beaker. Cool to crystallize. The crystals you'll get here will be tiny and powdery because they'll form rapidly with a lot of nucleation. The large dark crystals you saw earlier in this video were formed slowly over a long period of time. Swirl the beaker with product and collect in a clean Buchner funnel with new filter paper. Again, make sure the filter paper is seated properly. Use the mother liquors to transfer essentially all the precipitate into the Buchner funnel. When all the product is in the funnel, put a filter paper on top and press out any remaining liquid. Finally, stop the suction, remove the top filter paper, add some 95% ethyl alcohol, let stand for a short time, and turn on the suction. Again, in close-up, the ethanol helps remove impurities in water, and because it is volatile, it will speed drying. Let the product air dry with the suction on. When the product is dry, weigh an empty sample tube using an analytical balance. In using the analytical balance, remember to keep the doors closed and zero the balance first. Transfer the product into the sample tube. Do this carefully and gently to make sure you do not transfer any filter paper lint. And we weigh. Always close the door when weighing. You must label and turn in your product. Make sure your label has all the information shown. The label is the first thing someone sees when looking at your product. At the very least, it should be neat and accurate. Although this is not a quantitative experiment, you're expected to get a reasonably good yield and a product free from impurities such as charcoal or lint. Here are the calculations for percent yield based on our limiting reagent. Remember, 1 cobalt chloride produces one of the cobalt-3 complexes. Before we quit, here's a picture of the d electrons of this cobalt-3 complex jumping into antibonding orbitals in daylight. And as you well know, you would never do that in the dark. Boy, are they having fun. So, here it is, today's experiment. This and a whole lot of good chemistry